Having an injection is an experience common to us all, and whether you're unfussed by them or they make you feel faint, the actual needle used is the same for everyone and highly standardised. But given different parts of the body are more difficult to inject than others, this is not ideal. Scientists at Harvard Medical School realised this problem and have set about creating a more adaptive solution that could lead to big changes in healthcare. I'm Jack Taverner, and I spoke to Jeff Karp, who co-authored the study, about the challenges his team faced.
Needles have been used for over a century in medicine, but there really hasn't been that much innovation that has occurred in the last century or so. And so what this means is that often you're putting a needle through multiple layers of tissue to get to a blood vessel or a target space. And what happens is that there's a lot of variation from one person to another. And this can make it challenging for someone who's just basically placing these needles based on touch to get it into the right location.
So then how have you gone about solving these problems?
We've developed an auto-stop needle that can better target sites in the body, so the needle will automatically stop when it gets to its intended location, which can be used for drawing fluids like blood or delivering drugs. Our needle looks very similar to a regular needle. We just have a little, almost like a modular type design. So we've developed this so it can simply be attached to any needle, or we could actually make it standalone. And the way it works is that we will insert that needle to a location right before the target. And that location often is a very dense tissue where the tip of the needle will be clogged. And as you push on the plunger of our needle, what happens is the needle will advance. It's actually, the needle is moving in response to pushing on the plunger, which is very different from a standard needle. And when that needle then enters the target cavity, the fluid will actually come out the tip of the needle like a standard needle into the target cavity. So our needle automatically stops.
So which body parts have you been targeting specifically then?
We decided to go after one of the most challenging sites for a needle in the body, which happens to be in the eye. It's very difficult today to target drugs to the back of the eye. It's actually very important to be able to do that for diseases such as macular degeneration and diabetic retinopathy. And our eyes have multiple layers. And you can kind of think of those two layers as almost like a balloon inside of a balloon. And those two balloons are essentially touching, but they're not attached. And so what we were able to do is show that when you put the needle into the outermost tissue, so if you imagine going through that outer balloon, our needle will automatically stop when it transitions in between those two layers. So the fluid that we have in our needle will actually go in between those two tissue that's, on the order of 5 to 10, human hairs thick.
And in terms of the implications of this going forward, you mentioned the eye, that's one application site. Are there others, other uses for the needles?
We've shown that this needle device can also be used for epidural anesthesia. And the reason why that's important is that when placing epidurals, if you go too far, you get spinal fluid that can leak out. And this has caused really a lot of complications, a massive headache, and it requires a number of procedures to deal with that. We've been able to show in certain models in my laboratory that our needle can better target exactly where the needle needs to stop to deliver the medication. And so we can reduce overshoot injuries and reduce complications. We've also been able to demonstrate that this can work through targeting tissues just underneath the skin as well. And so there's a wide number of applications that we think this new technology could be useful for.
And in terms of the future then, are these going to be something that we are seeing in the coming months or years perhaps?
We've demonstrated that this needle can work in a number of medical applications. And the next step now to move this into hospitals would be to demonstrate specific disease indications where we want to deliver certain drugs. And then once we demonstrate that this can be effective, then we'd be able to move it to patients. And we think that we probably could do that within the next 2 to 3 years.
That was Jeff Karp discussing his paper published in Nature Biomedical Engineering.